Alright, thanks for watching, and today I will talk about closed sets, which has to do with limits of sequences. So, as before, let SD be a metric space, and let E be a subset of S, and then we say that E is closed if, whenever you have a sequence Sn in E, so whenever Sn is a sequence in E that converges to some number S, so it converges to some limit S, then that limit is also in your set E. Then S is in E. In other words, closed sets, they contain the limits of any sequence in that set. In other words, it's not possible to escape the set E by taking limits. So if Sn converges to S, then that limit S is also in E. And this is best explained with a non-example. So let me give you an example of a set that's not closed. So non-example 1. Consider the open interval 0, 1. Then I'm claiming this is not closed. What does it mean to show it's not closed? It means that you have to find some sequence in that set whose limit is not in that set anymore. And in fact, how about we consider the sequence Sn to be 1 over n. Let's say with n is greater or equal to 2. Then, well, that sequence is in your set 0, 1, but the point is the sequence converges to 0, which is not in your set anymore. Then Sn is in 0, 1, but Sn converges to 0, and 0 is not in your set. So in this case, it is possible to escape the set by taking limits. Just like escaping a very bad place in some sense. And this is not true for closed sets. Closed sets you cannot escape by taking limits. And by the way, similarly, we can show that the interval 0, 1 and the interval 0, 1, so here closed 0, open 1, open 0, closed 1, are not closed. And this is actually very important. So I want to emphasize the opposite of closed isn't open, because this interval is not closed. However, for example, this interval is not closed, but it's not open either. So there are sets that are neither open nor closed, but also there are sets, turns out, that are both open and closed. Those are called clopen sets. All right, but now the question is, what is an example of a closed set? Well, for instance, you have the interval 0, 1. Well, that one is closed. Because the point is, if you take any sequence in the closed interval 0, 1, then the limit of that sequence is also in the closed interval 0, 1. So you cannot escape the set by taking limits. But for instance, there's another thing. So in general, the closed ball Bxr bar, which is the set of points y in S, such that the distance between x and y is less than or equal to r. So again, just a closed ball as you know it. So xr. So everything here, including the boundary, this one is also closed. So if if you have any sequence in that closed ball that converges to something, the limit is also in the closed ball. And last but not least, a very strange set that I talked about before, I believe in section 11, and I covered it in another video. It turns out that if you have any sequence, the set of limit points of that sequence, or the set of subsequential limits of that sequence, is also always closed. So if S is the set of all subsequential limits, so the set of all destinations of express trains of Sn, subsequential limits of Sn, then Sn, then S is closed as well. And that we have shown this in a previous video. Then S is closed. Alright, so that's one thing. And now, remember I said before that, well, the opposite of open is not closed, isn't necessarily closed, but however, we do have this nice relationship between open and closed sets, and it's the following fact. Namely, E is closed if and only if its complement is open. Okay? And the complement is all the points that are not in E. So for instance, here, let's take this closed set E. This is equivalent to showing that the complement, so E complement, is open. So they're equivalent, in fact, in topology. That's how you define closed sets, saying that the complement is open. And let me prove this, and feel free to skip to the rest of the video if you're not interested or if you don't have time in my class. But by the way, I might ask that on a homework problem, so it might be worthwhile to watch this. Alright, so now let's move on with more general properties of closed sets. First of all, closed sets, just like open ones, they behave very nicely with unions and intersections. So properties. First of all, the intersection of any number of closed sets is closed. And you can prove this simply because, first of all, a set is closed if and only if its complement is open, and also the union of any number of open sets is open. So it's a very nice exercise that you should try out. And moreover, what we have that the union of finitely many closed sets is closed. And let me give you a counterexample for the infinite case. So non-example. In general, the union of infinitely many closed sets is not necessarily closed, because if you take un to be the interval 1 over n and 1, and let's say for n greater or equal to 2, then, well, let's see what those sets look like. So u2 is just 1/2 and 1. So that is u2. u3, it's 1/3 and 1. u4 is 1/4 and 1. And no u5, because in Austria there's no u5 anymore. Inside joke. Anyway, and then the question is, what is the union? Well, look, so the union is, it contains 1, of course, but also it kind of goes to 0, but the only issue is 0 is not in the union because 0 is not in any of those sets. So in fact, the union is just the open, half-open interval. It's the interval 0, 1, but this is not closed. So in general, you have to be aware of that. And moving on, so just like for open sets, we have interior points and the interior of a set. For closed sets, we have what are called limit points and the closure of a set. So definition. So we say S in E, so we say S, not necessarily in E, is a limit point of E if there's some sequence Sn in E that converges to S. S. In other words, a limit point is just a possible destination of a train in E. So if this is E, then we say, for instance, S is a limit point if you can find some sequence Sn that converges to S. And the set of all limit points, we'll call it E bar, or the closure of E. So the set of all limit points, so the set of all possible destinations of trains in E, all limit points of E is denoted by E bar, or, well, the book for some reason writes E minus, which makes no sense in my opinion. So the set of all limit points of E is denoted by E bar, and that's sometimes called the closure of E. So in other words, E bar is just the set of all places you can go by taking limits of sequences. So in general, it's this huge set. So that contains E and also usually its boundary. Not usually, in most cases I would say. All right. It always contains a boundary, sorry about that. So for instance, let me do a couple of examples of limit points. So there's some interesting ones. For instance, the limit set of all limit points of 0, 1. Let's see what this is. Well, you can definitely attain 0 by using a sequence in 0, 1. So 0 is in it. You can also attain 1 by using sequences in 0, 1. But then also anything in between is also a limit by just taking constant sequences. So in fact, the closure of 0, 1 is the closed interval 0, 1. Moreover, for the open ball, and be very, very careful, this is only true actually for RK. So in RK, the closure of the open ball, again this thing, so X and then RK. So if this is the open ball, BXR, then the closure is actually the closed ball, meaning all the points that are a distance of less than or equal of R away. So BXR closure is this. So BXR closure is the set of Y in RK where the distance between X and Y is less than or equal to R. But be super careful, this is actually not true in general metric spaces. So there are some metric spaces for which this thing, distance less than or equal to R, is not the set of all limit points of the open ball. For instance, and there'll be a video on this, but it doesn't work for the discrete metric, for instance. Alright, and moreover, let's see what the closure of the rational numbers is. And that's super, super interesting. Because you see, the rational numbers are a pretty dusty set. It looks something like that. But now, remember this beautiful fact. If I give you any real number, there's actually a sequence of rational numbers that converges to that number a. So recall, I think it was section 11, for any a in R, there is a sequence Rn of rational numbers that converges to A. So what does that mean? It means that it's really possible to attain any real number by using sequences of rational numbers. So actually Q bar, it's nothing else than the set of real numbers. Wow. Last but not least, what is the closure of the closed interval 0, 1? Well, the thing is, if you take any limits of sequences in 0, 1, you cannot go beyond that. So in fact, the set of all limit points is just 0, 1. And in fact, this is true for every closed set because any closed set contains all its limit points. So fact, E is closed if and only if E bar is E. That's very barbarian. Okay, and why is that closure important? So not only to check that points are closed, that sets are closed, but also it's used to define the boundary of a set. So what is the boundary? You should really think of it as what the skin is to the human body. So what is the skin? It's your entire body minus your flesh. So in fact, the boundary of E is just defined to be the difference between the closure and the set of interior points. So if you have this set, E. So it's hard to draw, but suppose the interior of E is this, E bar, and then for some reason the closure of E is that really thick set. Then the boundary is just the difference between the closure and the interior. So this is a set with a really thick boundary, but in general it looks much thinner. So in general, if this is E, then the boundary is just the skin here. I think almost like the sphere, but it's not always true. Alright, so for instance, let's calculate the boundaries of some sets. Last but not least, why is this closure so important? It's because it allows us to define the concept of a boundary of a set. Now, the boundary of the set, it's like this, what the skin is to the human body. So what is the skin really? It's the difference between the entire body and your flesh. So, I guess flesh and bones. And so in general, the boundary of a set, that's nothing else than the difference between the closure and the set of all interior points. So, for instance, if you have a set E like that, the interior is just whatever is inside. Okay? So that is E circle. And the boundary, closure, it's sort of, actually by definition almost, the interior with the boundary. So the E bar, it's this whole thing. And the the boundary is just the difference between the two. So usually just this green curve here. Although sometimes boundaries could be much thicker, and we'll see. So if you want another picture, think of this as being the interior and this whole thing as being the closure, then the boundary is just this. So for very thick-skinned individuals. So now let's do just a couple of examples with this. So what is the boundary of the interval 0, 1? Well, let's see what this is. So by definition, that is the closure of 0, 1 minus the interior of 0, 1. But then 0, 1 is closed, so it's just 0, 1. And the interior is just the open interval 0, 1. And well, what happens if you remove the open interval 0, 1 from the closed interval 0, 1? Well, then you're actually just left with 2 points. So if this is 0, 1, and you remove this thing, 0, 1, then you're just left with 2 points. So we're just with 0, 1. Which makes sense, because 0, 1 are kind of the endpoints of your interval. And here it's also sort of the endpoint of your set. Okay, and then, more interestingly, so again, this is very important as it's just for in RK. So usually the boundary of a ball in RK is just the sphere. So the boundary of BXR, that is the difference between the closure and the interior. But the open ball is open, so that's just BXR closure minus BXR. All right, and again, what is BXR closure? That is the set of all points which are a distance at most r, but maybe equal r away. So that is BXR closure. Again, think like less than or equal to r, and BXR is less than r. So the thing inside. And so, the boundary here, again in RK, is just the sphere of radius r. Things that are a distance exactly r away. Because this is less than or equal to r, and this is strictly less than r. So the only things that remain are as if things are equal to r. So this is a set of y in RK, such that dxy equals to r. But careful, this is generally only true for RK. There are counterexamples in, for let's say the discrete metric where the boundary of the ball is not always equal to the sphere. There's a video on that. Last but not least, let's calculate the boundary of the rational numbers. And it's quite surprising actually, I wouldn't have thought it would be this way, but what is the boundary? What's the difference between the closure of the rational numbers and the interior? But in this video, we found that the closure is the real numbers. And now the interior of the rational numbers, that's empty, because no rational number contains a ball that is inside the rational numbers. And therefore, the difference is just r. So again, if this is the rational numbers, the boundary or the skin of the rational numbers is the real numbers. And wow, that's thick, isn't it? All right, thank you very much.